Morning, everyone. So over the last 2 days, we've been introducing ionic nomenclature, basically the rules set with naming metal and non-metal compounds. Part of what makes it hard is they might throw in, oh, this one here is an acid, oh, this one here is a hydrate. They might throw in the odd covalent compound here. You first need to recognize what type of compound it is, and then do the appropriate naming from there on out. So just do a quick practice here. You need to be comfortable going from the symbols to the word name, as well as the word names to the symbols. We'll come back to this activity series in a second here, but just as a quick warm-up here. Let's see if we can name the compound here. I'm going to go Zn. We're going to throw on a PO4. So I'm going to work with the charges there. Zn3, PO4, 2. Let's do a SEI4. Let's do HBr. I want to know what's the formula for methane. I want to know, let's do iron 3, arsenite, and one more. Let's go nickel 2 nitrite. Alright, so again, for the time being, you can still use the table from grade 11 and grade 12, but eventually you do want to memorize those polyatomics. I would pause this video here, give it a go. They're all just sort of mixed up here, and then we'll see how we do. First one, going from the symbol to the word name, we recognize it to be ionic because I recognize it's metal. In this case here, the metal here is zinc, so zinc. Nicely, they put the brackets around the polyatomic to say the entire grouping is being doubled. This polyatomic here has the common name here, phosphate. I'm not going to change the ending on ATE. That's it. That's the name. Don't come and suddenly go tri-zinc or diphosphate or anything like that. Prefixes were only true for covalent compounds. That's something like the second one here. Oh, I noticed that Se is actually not a metal. So this is a non-metal, it's covalent. I can more easily just switch over to the covalent name, use those prefixes. I would have called it monoselenium. First mono I can drop. So let's make this here selenium tetraiodide. For both covalent and ionic compounds, the second non-metal we do change to IDE. So that part there is not differentiating. However, if you see a prefix, chances are you're going to be covalent. HBr here, we would have just simply, oh, easy, hydrogen bromide. But because it does have an H, we recognize it to be an acid. This one here is a binary acid because this is a two-part acid. It's not based off a polyatomic. So this one here had the structure like hydrochloric acid, hydroiodic acid. In this case here, it's going to be hydrobromic acid. So that's for a binary acid. Don't leave it as hydrogen bromide. We come to methane. We're like, how could we possibly know that? It's just the same way I say, well, how can you possibly know water is H2O? The more you use it, you just memorize them. So methane here is a natural gas. So methane is actually the formula CH4. That's a common name. Ammonia is a common name. NH3, acetic acid, we are CHQ. So there are a couple groupings that you do want to memorize for yourself. Iron, arsenide, I just wanted to give you one that was fancy here. Iron is the element Fe. Fe has a charge of +3. They're actually helping you out by giving you what the oxidation state is. Arsenide looks like arsenic. And arsenic here actually itself has a -3 charge. It's 3 away from the noble gas. So in that case there, if I work out the ratio, I just need one of each. By ratio, it's just going to be 1 Fe to 1 arsenic. So that's going to be iron 3 arsenide. Nickel 2 nitride here. Nickel is, again, it's given to me as a +2 charge. They're helping you out. What's nitride? Again, the hint here is if you see the ending IDE, it's probably elemental. The element that looks like nitride is nitrogen. Nitrogen is 3 away from the noble gases. I'm going to predict that it's N minus 3 like that. So the subscripts that I would need is for every 3 nickels, I would have 2 nitrogens. Capital letter for any symbols, 2 letters, the second letter is always lowercase. All your ionic compounds end up forming lattices. They just indicate the ratio in that formula unit. A covalent compound, so far I've only given you 2 covalent compounds. This covalent compound, SEI4, really is just a grouping SEI4. Methane really is just CH4. It's not, oh, it's actually repeating lattice and it goes over and over. It's just individual and it's just molecular. So again, the challenge for that section is it was all sort of mixed up in there. You need to know what type of compound it is. First question I would ask is there a metal? If it's a metal, non-metal, it's probably an ionic compound. Is the metal an H? If the first one is an H, it's probably an acid. If the ending is AT or ITE, it's probably having to do with polyatomics, which you need to memorize. If the thing is a transition metal, you would typically have Roman numerals. Now what we're going to do is, with that context, with that background of naming in mind, we're going to switch over and we're actually going to look at chemical reactions. This is the fun part of chemistry here, where we actually look at changes in compounds. So we're going to say reactions, chemical reactions. Sometimes I just say RXN for short, for reactions. These are actually reactions changes that you saw in Science 10, but again, just to make sure we're all on the same footing as we go here, I want to make sure that we're all on the same page. For a chemical reaction, we are starting with reactants. These are the ingredients that go into react, go into combine, and basically the reactants somehow change and they produce our products. So using an analogy, let's say I did some baking here, the reactants are sort of like my ingredients, and then the products are the cake. The products is whatever I'm making. Although we will take a look at balancing in a second from now, if I took a look at the ingredients making up the cake, the sugar, the flour, the icing, what have you, those things here, although they still are reminiscent, they resemble, they're still parts of the product, you wouldn't eat these raw ingredients here. The reactants here actually change and actually bond in different ways to end up forming your products. That's why, even though we will do balancing later on, I don't want to see reactants equals products. I actually want you to use an arrow to show me, no, reactants are actually combining, switching, decomposing in different ways and ending up changing into something that's totally different. That's why we had the arrow instead. We have 6 simple types of reactions. We'll do 3 today and 3 tomorrow. The first type of reaction here is called a synthesis reaction. Synthesis can also be called a combination reaction, and that says it all. We're basically dealing with a combination. Things are combining, things are joining together. A synthesis here, we can use S for short. A synthesis would just be taking A and B. When they change, they're just going to come along and they're just going to become AB. Usually, the A is an element. Usually B is an element, although it's not impossible for it to be a compound and a compound. If the compounds are tiny enough and they can also synthesize and switch together, in that case there, they can also be a synthesis reaction. So, I'm going to start off with what's referred to as a word equation. This is an equation. This is a sort of a statement of what the reaction is going to look like, and it uses the chemical words for all the chemicals. So my word equation here, just as an example, let's imagine taking magnesium ribbon. We saw this on the safety video here. Magnesium ribbon is actually burnt in a Bunsen burner. It actually reacts, don't say plus fire. Fire is not a chemical. Fire is just the energy source just to get it going. Magnesium ribbon actually burns with oxygen gas. And the question here is, well, what do we get? Those are the ingredients. If it's a simple enough reaction, I should be able to predict what happens. It's a little bit hard to identify just from the word equation itself, so we're going to use that trusty naming and the symbols that we've been doing. Let's write out the corresponding symbols, and let's see if we can get sort of the formula way of writing it. So in this case here, magnesium, by telling you magnesium ribbon, doesn't change the fact that it is magnesium. So you look on your periodic table, magnesium is the symbol Mg. Now earlier when we were doing naming, we would right away say, oh, magnesium is alkaline earth metal +2. Notice this is magnesium. It doesn't look like it's bonded with anything just yet. So this one here, I want to remind you, this magnesium is actually a no charge. It's actually perfectly happy having those 2 valence electrons because it wasn't used for bonding just yet. Because it is in this ribbon state here, because I can just hold it into the Bunsen burner, I can put bracket S just to say it's a solid. Similarly here, it's going to react with oxygen gas, so I'm going to say plus. Oxygen here, careful, was one of those diatomics. Whenever oxygen is by itself, it wasn't stable just as a single O like that. It had to appear as an O2. By telling you that it's a gas, it's just identifying, oh, it's just oxygen. It's not oxygen bonded with anything like that. You could put the bracket G for gas there. So that's the reaction I'm interested in. Throughout this section here, we're interested in sort of 3 keywords. We're interested in, based on this type of reaction, can we make a prediction? Can we guess what's going to be on the other side? can we classify what type of reaction this is? So far we only have the one type. It's called the synthesis reaction. It's going to be one of 6 types of simple reactions that we look at. And then can we come back and balance it? We'll see why we need a balance with this example here. So in this case here, we have elemental magnesium, we have elemental oxide, even though oxide was a diatomic compound like that. Because these two things are just by themselves, we would imagine, well, the cake is going to be part magnesium and part oxygen. As a general rule, these numbers don't drag over. So just because Mg is a 1 and Mg1, O2 don't drag over the numbers, you can always check the compound itself. I expect to form a compound of magnesium oxide. Something with magnesium in it, something with oxygen in it. So magnesium oxide, metal comes first. But do a double check for yourself, have I written this compound here correctly? Well, now magnesium is actually bonding. Now magnesium takes on its +2 charge. That's when I worry about the oxidation state or the charge, combining capacity. Oxygen has a charge of -2. Oh, great. It actually is the correct compound with MgO. That's why I say in general, those numbers there don't drag over. This one here is an ionic compound. If I demonstrated this for you here, you'd be able to tell me that it's solid. Not the end of the world if you don't have that there. Let me just draw a quick picture of this here. Something is not making sense. Magnesium is just a 1 atom. Oxygen was unstable. It had to be a diatomic. It was like a green atom combined with a green atom. And here we are saying the red atom has now bonded with the green. First thing we want to confirm is, has a chemical change happened? Have we actually produced something new? Well, sure. Chemical change, since the OO bond is broken. I came along and I actually separated. Previously, the O was attached to another O. I snapped that bond there. And previously, the red had nothing to do with the green. The red had to attach to the green. So chemical change, since this OO double bond is broken, and a Mg to O bond is formed. That's all that's actually happening in a chemical reaction. We end up forming, even though the magnesium is identical, the oxygen is identical, we end up calling it a new substance because they've been combined in a different ratio, they've been combined in a different proportion. Now that it has a different mix, now that it's bonded in a different fashion, it's now a totally different compound. So that's what constitutes the chemical change. Some bonds broke, some bonds formed. And yet, based on this picture, we want to see that even though there is a chemical reaction, the atoms remain unchanged. If I took a picture of this red atom before and I took a picture of the red atom afterwards, it's the same red atom. If I took a picture of the green atom, it's the same green atom. It's not that atomically, it's not that the element itself has actually changed. All that's actually changed is some bonds broke and some bonds formed. So based on that, however, if the atoms remain unchanged, what's not making sense is the numbers aren't matching up. So I have one red, one red. I have 2 greens, but suddenly I only have 1 green. Where did the other green go? In science, we have a law called conservation of mass. Let me just write it down for you here. So mass conservation or conservation of mass. When we say in science something is conserved, we say mass cannot be created or destroyed. Whatever amount of material I had to work with before and after has to stay the same. So mass cannot be created or destroyed. Yes, we will see it later on, mass can be converted into energy in science, but pretty much for us, we're going to say this picture doesn't make sense. If I weighed out my reactants, it might be, let's say, 100 grams. If I weigh out my products right now here, maybe, 60 grams. Oh, where did that extra 40-gram difference go? So in this case here, we're using the language, well, the mass of the mass of the reactants should always equal the mass of the products. Right? That's what mass conservation says. So how do we fix this issue? How do we address the notion that, oh, I actually need to have the 2 green atoms? Can I come along and just suddenly add a 2 here? Well, no, because I already worked out, based on my charges, the correct compound in the lattice is for every 1 magnesium with +2, it just needs 1 oxide with -2. Sure, it is a lattice. Sure, it is millions and millions of magnesium bonded with millions of oxygen, but at least by ratio, it's 1 to 1. What we can do in this point here is we can actually add coefficients. Coefficient is a fancy word for a number. Coefficients are numbers that I actually add in front of the compound. Because I've already confirmed my subscripts are correct, my compounds are written correctly, what I can do here is I can actually play around with the ratio. What I'm doing here is I'm actually doing the step of balancing. I'm trying to make sure that mass conservation is obeyed. And in this case here, what we're saying is, although the recipe does say, take magnesium, burn it with oxygen, it forms magnesium oxide, a recipe doesn't always mean an equal part sugar, an equal part flour, equal part icing, it's going to make a cake. You can actually play around with different proportions in the recipe. The nice thing in chemistry is because we know the before and after, we can actually predict the proportions. Now, there is no one right way of doing balancing. You're going to find that the more practice you get, the better you'll be. There are some hints, however. Some things I'm going to look at here is I'm going to leave the elements till the end, because if later on I come back and I change the number of elements, that only affects that one element. It doesn't affect two elements at a time. So that's one hint for yourself. Leave the elements to the end. The other one here is if it's an even number, diatomics will always be an even number on one side. An even number will never match an odd number. So what you usually do here is you'll take your odd number. Well, since I need 2 green atoms, let's put a coefficient in front. Let's put a 2 there. Now you'll notice what I've done here is in the recipe, the compound is still 1 red to 1 green. The compound has remained unchanged. I've still obeyed the naming rules that we did earlier. But all I'm saying is in the recipe, we actually create 2 magnesium oxides for what I put in. Now, I now have 2 green atoms. That's accounted for the 2 green. By putting a 2 in front of the compound, I've also screwed up the reds. Now I suddenly said matter came out of nothing. Well, it couldn't. Well, what if I actually put another 2 here? In this case here, well, if I have 2 reds, now at least, sure, the bonding is totally different. Previously, the greens were by themselves, and later on they're being attached. At least the number of atoms remain unchanged. Chemists are super lazy. If it is a 1, you don't need to include this one here. Although you want to be careful how questions are usually worded in the section. It's nice to you if they put it sort of in order there. It's nice to you if they say, oh, option A, which of the coefficients here will actually balance it? Just looking left to right, they might say 2 to 1 to 2. Just make sure you note that there's a 1 there. What IB likes saying is it actually asks you for what are the sum of the coefficients. So sum, so just another way of asking. Sum of coefficients. Remember, coefficients was just that fancy name. It's a number that comes in front just to make sure it balances. Sum of coefficients, they might specify all of the coefficients. What are the sum of the coefficients? The whole reaction. Once you've done your regular balancing, once you have your 2, 1, and 2, add them all up. Look for the option that says 5. Or maybe they say, what is the sum on the reactant side? 2 plus 1. Or is the sum on the product side? Just 2. You still do your balancing the same way, but when you go to actually find your answer, you add up the ones that they're looking for. Be careful to add every one that I don't show. So that's our last step there. We want to make sure for any balanced equation, we want to make sure that mass is conserved. We can play around with the recipe. This doesn't mean that you have to only react 2 magnesiums. Let's say I go to the store and I have 200 magnesiums. It just represents a ratio. Well, for every 2, you need half the number of oxygens. If you had 200 magnesiums, you need 100 oxygens, and I can predict you'll get 200 of the magnesium oxide out. That was a chemical change again. Some bonds broke, some bonds formed. Another way of saying that is you have some electron rearrangement. So that's what a chemical change is. We have an electron rearrangement. Electrons are going to make the bonds for us here. Electron rearrangement. That's how we produce a new substance. The atoms themselves stay intact, especially with this balancing. We made sure the numbers matched up. That one there was a synthesis reaction. Again, we can just bracket S for short. Let's do the opposite of a synthesis reaction, which is a decomposition reaction, which is a falling apart reaction. A decomposition reaction involves taking something AB. It's going to fall apart to become A and B. Really easy to recognize because we only have one chemical on the left-hand side. It doesn't have anyone to combine with, doesn't have anyone to swap partners with. It's just itself. In this case here, I'm going to start off. Let's do NH3, and I just have an arrow. Again, our 3 keywords. Can we, at this point here, make a prediction? Can we classify what type of reaction? In this case here, decomposition D. And can we balance it to make sure all the atoms are conserved? So balance. So we have this one here. You should know the common name. This guy here is called ammonia. So ammonia. So ammonia here. We see it's the only compound and it's supposed to be forming products here. If this falls apart, I would imagine it forms something with nitrogen and something with hydrogen. Do yourself a favor once you predict that. That's all the decomposition tells you. check whether I've written the compounds correctly. If it's ionic, check that the charges cancel out. In this case here, how does nitrogen and hydrogen appear to us when it's in nature? Well, these ones here are now nitrogen gas, hydrogen gas, they're by themselves. These ones here were hot wrinkles. These ones here had to be diatomic. So make sure you have those two there. Those subscripts are now, you can't change those. I know some teachers like, in terms of balancing, they like sort of laying out a table. They like saying, well, let's keep a tally of nitrogen, hydrogen. Essentially, this is a nice way of bookkeeping, but I find that it's a little bit too slow. At the moment here, I have 1 N and 3 H's. I have 2 N's and 2 H's. I see that the number of atoms don't match up. Again, I have even numbers. I'm going to leave my elements to the N. Maybe I'm going to double the odd number. By doubling this one here, the N goes to 2, the H goes to 6. Now the N's are good, so that's fine, but the H's are not fine yet. So I have a 6 there, so maybe I'll need a 3 in front. You do your regular balancing, and then they may ask you, what are the sum of all the coefficients? 2 plus 1 plus 3, 6. What are the sum on the product side? 1 plus 3, 4. I just find, again, this is being a little bit too slow. You're going to want to get enough practice that you can just do it purely by inspection like that. Sometimes decompositions don't go fully. So if you've ever seen elephant toothpaste, hopefully I can demonstrate this for you here. On a prediction, you might say H2O2, if it falls apart, I expect something with H and something with O. You would be totally fine at guessing H2 and O2. It's just that I've actually done this reaction here. I've realized the decomposition doesn't go fully to the H2 and O2. In fact, for a more complicated decomposition here, we actually end up forming water and O2. So in that case there, our prediction would have been wrong. That's fine. We're just guessing anyways. But in this case here, if I actually hinted at, no, we actually really get in this reaction water and O2, what are the balance coefficients that we need? Again, what I would do as hints here, I would leave the elements to the end because that would only affect the oxygen. In this case here, I have O2. This is an odd number. I probably want to double this one. Now I have 2 times 1, which is 2 O's there, plus 2 O's here. I only have 2 O's here. I need 2 times 2 makes 4. 2 times 2 for H's perfectly matches up with 2 times 2. If you're finding at any point here, oh, I changed this number, this one affects this one, oh, this one affects this one, and you're going back and forth, chances are one of your compounds are written incorrectly. This should be relatively easy to balance. So 2 to 2 to 1, the sum of all the coefficients is 5. You can draw a picture for that here, and you can confirm for me the number of H's match up with the number of O's. Let's end off with one last type of reaction. So far we've done synthesis, the combining. Decomposition was the opposite, it falls apart. The third simple type of reaction. These 6 that we do are not the only reactions that we can do, but these are the ones that are most common and the ones that we can guess. For a combustion reaction, by definition, combustion is a fancy name of saying a burning reaction, and the chemical you need for burning is oxygen. So burning with oxygen. If there is no oxygen present, the fire here should not be able to burn. So all those sci-fi movies that have explosions and fires in space here, that's all just total wishful thinking. Also for a combustion reaction, typically these ones here usually release much energy. So release energy. And the terminology you might recall, we call that an exothermic reaction. If you have to guess, combustions are always exothermic. The nice thing about a burning reaction is when we're making a prediction, 3 out of the 4 things I'm going to write are always going to be the same. For a combustion reaction, you take whatever the thing you're burning. We said it needs oxygen. So I'm going to go say plus oxygen. Oxygen is a diatomic, so it's going to be plus O2 like that. Upon burning, I'm going to assume you're burning things with, so this is the species that's being burnt. Usually the species being burnt will be some number of carbons, some number of hydrogens, maybe even the odd oxygen around. You could hypothetically burn nitrogen, sulfur, things like that as well. But because there's carbons and hydrogens going into it, we're going to make an assumption here. When it's a reaction with oxygen, it looks like a burning reaction. We're going to assume something called complete combustion. A complete combustion will happen when the fire has been raging for a little while, when there is enough oxygen applied to the fuel. The oxygen ratio should follow the balancing that we're going to see in a second here. Upon a complete combustion, we can go straight to say this is going to form CO2 and this is going to end up forming water. Those are the fully oxidized, fully burnt up products after you burn up the species. So take any compound, 3 out of the 4 things are fixed. If you see it reacting with oxygen, chances are it's a combustion, and you can right away say CO2 and water. Just a quick what if here. What if we actually had partial combustion? They might say partial combustion, they might say incomplete combustion. If the combustion is incomplete, as the name suggests, maybe there's not enough oxygen around, maybe the fire is slowly dying out or it's just starting to get heated up. Instead of getting fully oxidized with CO2, I'm going to get some carbon. We would usually call that soot. That one is a solid. It ends up making a dirtier flame, a darker flame, because there's unburned material. Or we might end up getting carbon monoxide instead. This one here is a very toxic gas we want to be really careful of. So whenever we're doing this section here, predicting, balancing, classifying, we're going to always pretend complete so we can go fully to CO2 and water. Let's just do two reactions here. Let's take that natural gas. What if I said I have methane? I get another word equation. Methane is being burnt with oxygen. Can you predict, balance, classify? Well, methane was that common name that I wanted you to memorize. So methane is the sort of lightest hydrocarbon here. So CH4. It's just going to say CH4O2 arrow. You just need to recognize, oh, the thing we're burning happens to have C's and H's. We happen to have oxygen as the other ingredient. Right away, assuming that the combustion is complete, which we'll always do, we can right away say CO2 and water. I don't really care what you're burning. It's going to just fully oxidize to form CO2 and water. Now, in terms of balancing, we're going to say I have one carbon. We're going to utilize this more in chapter 1. The carbon all ends up in the CO2, whereas the hydrogen all ends up in the water product. So if I just match up those numbers, we should be good. I have one carbon, one CO2, perfect. 4 hydrogens. The waters only have 2 hydrogens, so I'm going to have 2 times 2, make 4. I've screwed up the oxygens now. I have 2 oxygens here, 2 times 1, another 2 oxygens. Oxygens come as 2, so 1, 2, 1, 2 will be a ratio. When I'm doing this balancing, the left-right order doesn't matter. I could have put 2 waters plus CO2. It just has to be on the right-hand side, the product side. So that's complete combustion. We'll end off with one last one here. Let's do ethane. Ethane is a slightly longer hydrocarbon here. Again, 3 out of the 4 things are fixed. If I tell you it reacts with oxygen, I can even put water first and CO2 first just to show you the left-right order doesn't matter as long as it's on the correct side. Let's do the same thing. We're going to have 2 carbons. Well, the carbons all end up as CO2. I need 2 there. I have 6 hydrogens. Hydrogens come as pairs, so I'm going to need a 3 times 2. Unfortunately, here looking ahead, the oxygen here is going to come as a diatomic. It's coming as even numbers. I may have an even number of oxygens here, but I have an odd number here. So if I totaled up the total number of oxygens, I would say 3 times 1, I have 3 O's. 2 times 2, end up making 4 oxygens. I actually have 7 oxygens. What I really want to say is something like 7 over 2. There will be something in chapter 5 that we actually leave it like that with fractional coefficients. What we're going to instead do here, we're going to be normal. We're going to say, well, since this is just a ratio anyways, let's just rescale it. Let's simplify it so that it's the lowest whole number ratios. In this case here, the only thing that was a fraction was this 2 here. If you are having trouble balancing, just double everything. 2 of your ethane would need 7 oxygens. This would then be 6 waters, and this would then be 4 CO2s. And in that case there, again, I'll make that note there, when we're balancing, okay, these coefficients, okay, balance with the smallest whole number coefficients. Because it is a ratio after at the end of the day anyways, so it doesn't mean you have to only react to, but it just gives you the proportion. For every 2 parts of this, you need 7 times oxygen, you get 6 parts water, 4 parts CO2. In fact, earlier we had a reaction with oxygen. Earlier we could have even said this magnesium oxide, this one tends to give off a really intense white light. You could have called this a combustion as well, but in this case it's a metal. This metal here has no carbon source. That's why we don't fully get CO2 and water. We get something with magnesium in it. I mentioned you could burn things with nitrogen, burn things with sulfur. Obviously, I can't just balance it straight with CO2 and water. I would need to say, oh, it makes SO2, it makes NO2. It's totally a guess at this point. I would need to actually go do the experiment and then analyze what I formed to see whether I got it correct or not. So practice through your worksheet with some predictions here. We'll finish off with the last 3 reactions in another lesson. Thanks, guys.